going, everybody? Welcome to CS540 midterm review. So first of all, hope you had a nice spring break. I know many of you might have some questions about the exam, so I just made this video to the midterm that we took just now in the spring midterm in 2019. Here are just some photos I took for my own paper during the exam. So I'll just do a brief explanation to all the questions here. So the first question, which of the following is true about the search algorithm, and select all the correct answers. So A is BFS is complete and optimum if all costs are equal. This is true. So you remember, if the costs are all just like a unit one, then it's actually it's complete and optimal. BFS is always complete, and if it's one, just optimal. B, the goal state returned by DFS has minimum cost from the initial state. This is not true, since DFS is not optimal. So DFS can just can make the space complexity simpler, but it's not optimal. C, space requirement for DFS is less than the BFS. That is true. The reason I just explained just now. Uniform cost search always find an optimal solution regardless of the edge cost, which is true, and that is just the definition for uniform cost search. The second question, consider the zero-sum game tree below. Denote this as the maximum and minimizing players respectively, and just cross out the branch that will be pruned by alpha beta pruning. So as we can see here, so for the node A here, actually here is a maximizing function. So the second layer here is the minimizing. So as you can see, actually I've drawn this kind of my calculation during the exam. So the alpha of A at the beginning is minus infinity and beta is infinity. So when it comes to B here, alpha is still minus infinity and beta is infinity. And when B comes to here, so since this is a minimizing algorithm, so it will just change the beta value. Since 7 is smaller than the infinity, so we just replace it with the 7 here, infinity. The alpha here is smaller than beta, so we'll continue. And when it comes to D here, we just D, since D hasn't have any values yet, so we just come here, and as you can see, D here is actually getting maximized value. So first of all, so the correct solution step is actually, first you replace the since D here, the alpha is still minus infinity, so you will replace the minus infinity with minus 6, and it will just compare minus 6 with 18. Since 18 is larger than minus 6, so the alpha value here is 18. However, right now the alpha value is 18, which is larger than beta value of 7. So if there are any other nodes after D, or just after the 18 here, the node here, actually they will all get pruned. However, since there is no any other node here, so nothing get pruned. So the node D here will get a maximum value, that is 18, and B will get a minimized value between 7 and 18, which is 7. So here when we go back to A from B, so A here is maximizing, so it will just change the alpha value, and since 7 is greater than minus infinity, it will just replace the minus infinity with 7. So right now the alpha value of node A has already get updated. Then from A to C, so just ignore this part first, since C hasn't get any updated yet, so you will just first come to this node minus 2. So C here is the minimizing algorithm, so it will just change the beta value. Since minus 2 is actually smaller then infinity, so it will just replace the beta value of infinity to -2. However, at this time, the 7, which is the alpha value, is greater than -2, which is the beta value here. So all the nodes after C will get pruned. So these parts just get pruned. The third question, which of the following is true about the heuristic function hs? Select only one choice. So the first is, if hs is always lower than or equal to the cost of moving from S to the goal, then A star is guaranteed to find the optimum path. That is true, since A star, actually the definition of A star is all the heuristic value are admissible. So this is actually the definition for the admissible. So if the heuristic value are admissible, then the A star is guaranteed to find the optimum path. B, if hs is admissible, the lower hs is, the last node's A star expands, which is absolutely true. Absolutely false, sorry. A very simple case is, well, we can just make all the hs, for example, equal to 0. Then there's no difference with A star with the DFS. So that does make sure that last node will A star expand. C, if hs is exactly equal to the cost of moving from S to the goal, then A star will only follow the optimum path and never expand anything else. It is absolutely true, since as we know, the A star is actually equals to hs, which is the heuristic value, plus the gs, which is the path from the initial state to the current node. So if the cost is exactly equal, the cost of moving from S to the goal, then it is exactly when, if you have the gs plus hs, then this value should be the exact cost from the beginning node to the goal. So since A star search will always get the minimum value for hs plus gs, so of course it is true, it will just find the optimum path. So both A and C are correct, so we just choose D. And for the fourth question, the graphics here, so it has two parts. The first part is to find the range for node A and B to get the range for the heuristic value h1 and h1 value in order to make it admissible. So first of all, if we want to find the range, we just need to know the maximized cost from the current node to the goal. So for example, the node A here, the minimized cost from A to F is actually from A to B, B to C, C to D, D to E, and E to F. So which is 2 plus 1 plus 1, 4 plus 3, 7 plus 2, which is 9. So the maximized value for the heuristic value for node A is 9. So A should be greater or equal than 0, but less or equal than 9. And for node, the same thing. So from B to C, D, and E to F, and we are able to get the minimized value for 7. Of course, since this graph is simple, so we can just get the minimum path from that node to the goal. However, if it's more complicated, we have to draw the diagram, but just to save time, we just do things. The second question is, provide the path returned by A star search using the heuristic value h2 here. So I've drawn the graph here. So first is A, and A has two children. One is B, the other is C, and their cost is 2 and 4 respectively. B, so I just skip that part. It's not very convenient to look two parts together. So the value besides node B here is just the heuristic value. So B here is 5. So as we can, and C is 12. If I'm C is 8. Sorry. Oh, B is 3, and okay, so what this means is the value besides the node is just the heuristic value plus the cost here. So B is 3 plus 2, which is 5, and C is 4 plus, I believe, is 8. Yep, 4 plus 8 is 12. Since 5 is more than 12, so we just chose B. So first is A, second is B, and B has 3 children, C, D, and E. So we can just draw like this and put the path cost here. So for example, C here, the heuristic value is 8. So that is 2 plus 1 plus 8, which is 11, so on and so forth. So next we are going to compare between the C, D, E, and C, the value C here. So between these 4 values, the minimum is the E here, which is 9, so the third node is E here. Then E got another 2 children. Then we are going to find, okay, so now is 11, 12, 16, 10, and 12. The minimal value is 10 here, so that is F. So the correct path is A, B, E, and F. Yep. So the 5th question I did it wrong. To be honest, even nowadays I search a lot of stuff. I really have no idea how to do this question. If any of you have any like hints or you guys have any explanation, I'll be very, very happy to hear that. So just leave comments below if you know how to do this question. The 6th question: in simulated annealing, one expects a transition from S to an inferior neighbor T with a probability. Okay, suppose Fs equals to 3 and F at T equals to 1. At what temperature is the transition probability of 1/3? So it's just a pure math. We just make this Fs is 3, 3 minus 1 is 2, so the exponential term here is e to the power minus 2 over t, which if make it to be 1/3, then we can just use our calculator to just like make it out. 7th question, the graph is here. So I just skipped the reading for this question. So what is that? Actually, this question is there were actually totally there are n plus 1 nodes. So from S1 to Sn minus 1, they all have a children with S0 here. However, they got another children for example, S1 got another children for S2, so on and so forth. And Sn minus 1 have the children Sn here. However, since Sn is the last low node, so it just stops here. So the question asks, there is no cycle check nor closed list. How many go checks will be performed by DFS? Assume state with smaller index is checked first to break ties. So for example, the algorithm will first have S1, then to S0, then back, then S2, S0, back, S3, and so on and so forth. Since it says there is no cycle check nor closed list, so it won't check like whether I've checked S0 or not, nor neither it will check like, since here has no duplicate nodes except S0, so actually this condition is not important. So it will just check all of them. And since here has n minus 1 nodes, and each of them got a S0, so here we see 2 times n minus 1. However, don't forget the last node, which is Sn here, so we should plus another one, which is 2n minus 1 here. Here the question, I believe this is actually I think an example in our lecture note, and in my previous YouTube video actually I talked about this. So there were just like 2 chopsticks, so you can either take one or just take both of them, and the player who takes the last stick wins. So first of all, you can just take one, since no matter you take the first or the second, just like equivalent. So I just take the first one, and I just take the second one. And here another solution is just take both of them together. So let the game value be 1 if the first player wins, and -1 if the first player loses. So if first player wins, the game theoretic value, and calculate the game theoretic value. So as we can see, if the first player takes both of the sticks at the same time, so this will be 1. However, if this case, it will be 0. Oh, sorry, -1. So if you put -1 here, -1 here, since this is the maximize, so this is the minimize algorithm, this is maximize algorithm. So we just take the maximize value, maximum value, which is 1 here. So the theoretic value is both players play the balanced. So it will just take both of the sticks at the same time, and the value is 1 here. The ninth question, so here, actually the numbers here are just cost, and the value in the node is actually the heuristic value. So it actually asks the order for the states popped off of the open list when using a star search question here. So first is S. S has the heuristic value of 2. It has 2 children. One is A, the other is B. So from S to A here actually is 5, and from S to B here is actually 2 instead. And B here is just 7 plus 2, which is 9 here. So first, I just put left here. So this is the open node. So it actually asks the sequence that the node popped out of the open list. So first is A, and first is S, and S will append 2 node. Here one is A, the other is B, and of course it will just pop the S first. So the first is S, the sequence. And since A is actually smaller, which is 7, which is smaller than the B value, which is 9 here, so it will just pop A here, and the second just append A to the pop list here. Then A has 3 children. One is C, D, and G here. So A to C, the cost is 1. A to D, the cost is 2, and A to G is 4. So C's heuristic value is 2, and 2 plus 5 plus 1, which is A here. D is 1, and 5 plus 2 plus 1 is 8. G is 0, so we just 5 plus 4, which is 9. Okay, so here we also have C, D, and G here. Next is a question. So it says use the objective function, blah blah blah. If there are ties, please consider all possible combinations and provide all resulting paths. So as we can see here, actually we have C and D both equals to 8. So first of all, we can just pop the C here. If we pop the C, and C has A, has children A and G. However, A has already included, so we just have G here. A to G, the value here is 5. So 5 plus 5 plus 1, which is 10, which is 11. So the objective function of FG here is 11. Next we compare 11, 8, 9, and 9 here. Next will be D here. So we pop out D. And since A has already checked, so next is G here. So the value of G here will be 5 plus 2, which is, from D to G here, the cost is 1. So which will be 5 plus 2 plus 1, which is 8 here. And next we're going to compare the 11, 8, 9, and 9 here. Since this G node here has 8, which is the smallest, so we just have pop out G here directly. So the first solution is as A, C, and G. Let me just erase this. So next, after we have the condition for C, we are going to have another possibility, which is D here. So we first consider D, and D has 2 children. One is A, the other is G here, and from D to G is 1. So, and it is 8, which is 5 plus 2 plus 1 is 8. So first of all, we pop out the D. So the second solution would be SAD. Then we compare C, G, G, B here. However, there are another 2 8. So C has the value of 8 and G has the value of 8 here. So there are also 2 possible solutions. One, of course, we just append a G here. And the second possible solution is we just have the C first. So as a D, so instead of pop out the D first, we're going to pop out the C first. So C has children for A and G. A has already checked. So we have G, which is 5 here. 5 plus 5 plus 1 is 11. Then we're going to compare between G, 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 and B. So many G. Oh my God. So we take the smallest one, which is the 8 here. So we just compare append a G here. So actually we have 3 different solutions, and my answers here are actually wrong. Next, this question. In the given state space as the start node, what is the BFS, DFS, and uniform cost search return from the following search? So I can just do it here. So for example, if it's DFS, so which is from S to A to B to D to C and to G. So we can just like do it directly, since DFS will always find the minimum, the smallest node according to the alphabet sequence. And so just skip the BFS and use CS step first. I believe it's quite straightforward. I believe you guys can do that. So question 11 is going to compute the probability of the word type word W in the vocabulary. So the corpus has the token for 2 million different tokens. Suppose a word token W appears in the corpus 24 times and the size of the vocabulary is 10,000. Use L1 Laplace smoothing and give the expression for this probability. So we just in the denominator we have 24, since it appeared 24 times, and we need to plus 1 and divide by the how many tokens, which is 2 million, and we are going to plus the vocabulary size, which is 10,000, and we can, after simplify it, we just like get this answer. Question 12. Which of the following are true about representing document about TF and IDF? Okay, and select only one option. So choice A, stop words are handled by TF. If you look at this, the definition for TF and IDF here actually is stored by both the TF and IDF here. So A is not correct. B, importance of the word in documents depends only on the words that in the document. If you look at the IDF here, actually it also like have relevance to other documents, since we are going to find the documents that contain the word W here. Third choice, length of the document vector is the vocabulary size for the whole corpus. That is true. So for example, if you have like, for example, 10,000 vocabularies in the whole corpus, then your length of the vector is actually just 10,000. So the correct answer should be C. Question number 13. An n-gram language model computes a probability blah blah blah, which are true about the n-gram models, and select only one choice. So the parameters are estimated with Markovian assumption. So yeah, just in the PowerPoint here. Second, sparsity in a data set can be handled by Laplace smoothing. That is true, since when using Laplace smoothing, it just gets smoother. Laplace smoothing adds more mass to the unseen events while removing it from the seen events. That's true. So for example, if you have seen that event, the probability gets smaller. And if the event hasn't appeared in that document, for example, so the logical value should be 0. However, we make it like slightly larger than 0. So we just like remove it from the seen event and add it to the unseen event. Question 14. We flip a fair coin repeatedly. What is the probability that we have to flip it exactly 12 times to see 2 heads? So what the question asks is, when you flip the 12th time of the coin, you actually see 2 heads. So the 12th time that you flip it must be a head, and another head might be appear in any of the first 11 flips. So there are 11 different choices for the first so the heads can appear in the first 11 flip, and each of them are just like 1/2, and since there are 11, so we have to like times half by 11 times, so that is 1/2 to the power 11, and times 11, and times the 12th time that the coin will be a head, which is 1/2. So we get this value. Question 15. We have a bag with 3 fair dice, a 4-sided, 6-sided, and 8-sided die. We pick one die at random time and roll it twice. The first roll is 1 and second roll is 5. Given both rolls, what is the probability that 6-sided die were picked? So we can assume D6 is the 6-sided die we picked. So we can have the formulation here, which is P D6. That is what we want. And given the condition, so our condition can be assumed to be A here, which is the first row is 1 and the second row is a 5. So by using base rule, we are actually able to transfer it from here to this formula. So the denominator is both condition satisfied and divide by the condition of this A here. So when both of the conditions satisfy, one is we get a 6, the 6-sided die, and another is one is 1 and the other is 5. So if we want to get the 6-sided die, actually we just pick one of the 3 dice, so which is 1/3, and the first row is 1 and second row is 5. Since there are independent cases, we just like multiply them, and since there are 6-sided, so there are from 1 to 6 the value. So if we get 1, which is 1/6, and 5 is still 1/6. and the possibility that you are actually getting this the first row is 1 and the second row is 5. You can only pick from either the 6-sided or the 8-sided die. Since 4-sided die, the maximum value is 4, you are unable to get a 5 here. So the possibility of FPA here is you got 1/3 of chance get the 6-sided die, and times 1/6 times 1/6, and plus another 1/3 of chance to get the 8-sided die, which is 1/3, and times the 1/8 and times 1/8. And you just simplify this term and you are able to get the value here. So to be honest, compared to the last year, I think the midterm, I think this paper is much more difficult. I hope you guys did well in the exam, and hope you have a nice day.